conference. It's a pleasure to introduce Nayantara, who was a student at Georgia Tech, worked with my colleagues Dana Randall and Eric Vigoda, and she's now a Neyman Professor in Statistics at UC Berkeley.
Okay, thanks for staying till the last talk. So I'll be talking about extremality of Gibbs measure for colorings on trees. This is joint work with Juan Vera, who's at Waterloo, and Eric Vigoda, Georgia Tech. So I'll cover what the problem of extremality is and its connection with a problem called reconstruction and broadcasting. Oh, is the microphone working? Hello? Yeah? Okay. Oh, okay. Its connection with broadcasting on trees, and then I'll present a result saying that this reconstruction problem is not solvable on trees when the number of colors k is bigger than 2 delta over log delta. Delta is the degree of the tree. Okay, so I'll define everything later. Okay, so the model is that we have an infinite tree of branching factor delta, and we have a finite alphabet of size k, and the spin at every vertex takes a value in this alphabet.
Sorry, just one more question. So delta is the degree of each vertex, right?
No, delta is the branching factor.
So that's glad
yes. So every vertex has delta children. So every vertex.
So you think of it as a rooted tree.
That's right. Yeah.
And does that mean that the root has degree 1 less than everybody else?
Yes.
Okay.
Yes. I would think that everything goes through if you actually fix every vertex to have degree.
Yeah, I can't
delta.
imagine it would make much difference.
Yeah. Okay, and then we have, so we choose the spin at the root according to some distribution over the alphabet, pi, and then there's a broadcast process which works as follows. So there's an independent Markov chain on each edge of the tree, and it decides the spin at the vertex u given the spin at its parent I. Okay, so you start at the root and you start broadcasting in this way down the tree. So if we pick the initial distribution pi to be uniform over the set of colors or the alphabet, and set the probabilities so that they're all 1 over k minus 1, as long as I is not equal to j, then this will give rise to proper colorings on the tree. Okay? And you can also see that sort of each coloring is equally likely to arise by this process. So we want to sort of define what measure we get over colorings, and you have to be careful because you're on the infinite tree. So this gives rise to what's called a free Gibbs measure on colorings, and so a Gibbs measure for us will be a measure satisfying the following property. So if you look at sort of any finite subset of the tree, okay, and fix the coloring outside it, so let that finite subset be U, and fix eta on the outside, and then ask, in the measure, what's the probability of seeing sigma given eta, okay? Then this is just equal to 1 over the total number of proper colorings of the set U conditioned on what's outside, okay? So assuming that sigma agrees with what's outside on U, okay? This is the probability, okay? And so, okay, I guess the blue is not very clear. That's unfortunate. So Brightwell and Winkler showed that when the number of colors is less than or equal to delta plus 1, that multiple Gibbs measures can exist. And this is not difficult to see. So when you have this few colors, then you could have sort of a frozen configuration where the color is just determined by how your children are colored. So if your measure puts sort of all the mass on one of these frozen colorings, then that's certainly a Gibbs measure, and there could be multiple such frozen configurations. Okay. For the other direction, Jonassen, I'm not sure, showed that when k is bigger than delta plus 2 for a large enough constant delta, that there's a unique Gibbs measure. Okay. And we'll be interested in the regime where there are multiple Gibbs measures, so the number of colors k is less than or equal to delta, and you'd like to understand the following. When is mu extremal? So when is it not a convex combination of other Gibbs measures?
Mu is the free one.
Mu is the free one, that's right. Okay, and so one reason why this problem is especially interesting is that the question of extremality turns out to be equivalent to the decay of correlation between the information that you have at the root and the information at the leaves in this broadcast process. And I'll say precisely what I mean. So imagine sort of two copies of the process, one of which starts with red at the root and one of which starts with blue, and then broadcasts down the tree, and then you truncate at level L and take an observation of the leaves. Okay, so reconstruction is said to be non-solvable if for every pair of symbols that you start with, I and J, if you look at the total variation distance between the distribution at the leaves, conditioned on what you started with at the root, then this distance goes to 0 in the limit. Okay? And extremality of the Gibbs measure is equivalent to this difference going to 0 in the limit. Okay? All right. And what we'll do is reverse the conditioning that we have here. So here, what we're doing is conditioning on the symbol at the root and asking about the distribution at the leaves. But you can reformulate this by reversing the conditioning and say, let me look at the probability that the root is colored I given a random configuration of the leaves. So think of this quantity as a random variable which depends on the leaves when generated by this broadcast process. Okay? And you ask, how much does this random variable deviate from its expectation? Okay? And you want to know in the limit, how does this deviation behave? So if it goes to 0 in the limit, then this is equivalent to reconstruction non-solvability and hence extremality. And this is sort of the formulation that we'll work with. Okay? So
is it uniqueness of the Gibbs measure, is that equivalent to this going to 0 in uniform norm rather
that's equivalent to this going to 0 for every boundary that you take. Yeah, that's right. Okay, so just some motivation for why you might want to study, when you can do reconstruction comes from all sorts of areas like you might have models of evolution of DNA which propagate genetic information down a tree. You want to understand sort of the trade-off between how much information you're duplicating and how much you're losing because of errors. In information theory, and recently there's been some interest in the study of the solution space of random constraint satisfaction problems. And the second sort of reason for interest is that, so one result that Eric mentioned earlier was the polynomial mixing time of Glauber dynamics for the class of planar graphs when the number of colors is less than delta, so specifically order delta over log delta. And there have been results, so for example, Martinelli, Sinclair, and White showed that if you have this type of exponential decay of correlations, then this implies n log n mixing time for Glauber dynamics. This holds under the condition when you have uniqueness, but this is more because you're trying to compare with some block dynamics that this comes up. But there seem to be connections possibly with mixing as well. Berger, Kenyon, Moselle, and Perez showed that extremality is a necessary condition for very rapid mixing of Glauber dynamics. Okay, so here are the results that were known. So Brightwell and Winkler showed that extremality is true when k is bigger than delta plus 1. In the other direction, Moselle and Perez showed that reconstruction is possible when the number of colors is just less than delta over log delta. Okay? And the idea is that if the degree is large enough, then in this broadcast process you're going to sort of see you're very likely to see all but one of the colors as you go down. So if the degree is like k log k, then by coupon collector you expect to see sort of all the colors, and if this happens with good enough probability as you go down the tree, then given just the leaves, you should be able to reconstruct what you had, right? Okay, so the result I'll talk about today is showing extremality or non-reconstruction when the number of colors is just larger than 2 delta over log delta. And recently, Alan Sly improved our results and got very tight estimates for what the bounds for non-reconstruction as well as reconstruction are. So his bounds are sort of in terms of bounds on delta, and he gets rid of certainly this factor of 2 that we have here, but he also works out a lot of the lower order terms. Okay. So here's a statement of our theorem. So suppose that epsilon is bigger than 0, and delta, the degree, will be some large enough function of epsilon. So if k is bigger than 2 plus 20 epsilon delta over log delta, then we can show the following sort of concentration statement. So the statement is that when you choose, so this probability is going to be over choices of random boundary. So choose a random boundary, sigma L, look at the conditional probability of the root being the color C, okay? And look at the deviation of that from the expected value, which is nothing but 1 over k, okay? The probability that this thing deviates by more than delta to the power minus alpha L goes to 0 sort of doubly exponentially in this way, okay?
What is L as a number?
Well, L is the depth of the tree, and it grows, yeah.
It's not the exponential of the depth, it's the depth.
It's the depth.
The number.
Yeah, right. Okay, so this statement implies extremality because, well, yeah, okay, you see why, yeah, okay. All right, so let me quickly try to go through some outline of the proof. So a nice property of this free Gibbs measure is that it's invariant under automorphisms of the tree. So what I mean by that is, if you think of what the process does, it starts with a random color here and sort of propagates downwards. So if you ask at any one of these children, say, what's the probability of seeing red? Then it's exactly 1 over k, if you don't know anything about the root. So the sort of measure that you get here is exactly a copy of the measure on the larger tree. Okay, so so here's where this is written out. So so for trees which are rooted at the children, for example, the Gibbs measure is exactly the same as the original free Gibbs measure. Another sort of nice property is that when I truncate the process at level L, and I look at the distribution on of the colorings at level L, and say that's distributed according to sigma L, the subcolorings, so if I look at each of these subtrees, and I ask about the delta sort of subcolorings here, then these are distributed exactly as they would be if you truncated the process at level L minus 1. Okay? And what these kind of facts allow you to do is write a nice recursion for the Gibbs measure. So the probability of the root being C given some boundary x can be written in terms of the probability of various colors of the children given the colorings xi. Okay? And the point is that this is, again, the free measure. Okay, so recalling that the statement of non-reconstruction is this thing, our strategy is going to be to show that when we pick a random coloring x, then this recurrence will actually converge to the fixed point 1 over k with very good probability. Okay? Okay. So an outline in words. So the particular colorings which are going to converge with very good probability, we're going to call good, and they'll satisfy the following property. For every color C, if you condition on x at the boundary and look at the probability of the root being C, it's upper bounded by something a little bit less than 1 over square root of delta. Okay? And the statement is saying that when we pick a random coloring x from the Gibbs distribution, this event will happen with very good probability, this probability here. Okay?
So this is the probability that it takes a particular color C? If the root takes a particular color.
given x at the boundary, is upper bounded by
But
this.
don't those probabilities have to add up to 1?
They do, but we're just giving an upper bound. So this will add up to something bigger than 1, actually. So what we'd like is that this is 1 over k, but we don't know how to get that immediately.
Oh, I see. Oh, I see. This is.
It's like max.
Right.
Oh, I see. This is some number a little less than 1. It's not big.
Well, it's about square root of what we want to get. It's not close to 1, but yeah. Okay. So then the idea is we give a little bit away for this probability and say that in the tree above some level, so epsilon L, this same bound holds when we condition on x at every vertex, not just the root c. Okay? And once we have that, what we can argue is that if you look at this random coloring x and change the color of just one leaf, then the effect on the root, the effect on this marginal probability at the root is bounded by this thing, which is related to this bound raised to the power L. Okay? So think of it as you're changing one leaf distance L away from the root, how much does it affect the marginal probability? Well, it goes down exponentially like this. Okay, that's sort of the point. Okay, and then we use a martingale argument to say that, well, we trade off against delta to the L possible differences at the leaves, and we can show the concentration of this variable around its expectation, which is just 1 over k, right? And this is what we wanted to show. Okay, so now a little bit more in detail. So now I'm going to confuse everything and change the definition of good. So a leaf coloring is good if the same condition as before, but now we're bounded by epsilon. And this is just to keep things clean. So epsilon will be just a bit bigger than 1 over square root delta, the bound that I had before. Okay, and then here's the statement. So how do we prove that a coloring x is going to be good? So we're going to give a recursive condition. So x will be good if most of its subcolorings, so remember that there are these delta subcolorings at the delta sort of subtrees rooted at the children of the root. Okay, so if at most 2 of these xi are bad, so they don't satisfy this property, then we'll argue that x is good. So inductively, we just need to say, well, the probability of xi being bad is sufficiently small. Okay? Okay, so how do you argue this? So now x is just a fixed deterministic coloring. Okay? And you assume that at most 2 of the xi are bad. Yeah?
Can you see the definition of good?
Yeah. So good says that these marginal probabilities are bounded by epsilon. We're going to use this hypothesis on the good xi to show that this marginal probability will actually be bounded by this factor 1 over square root delta. And then that will turn out to be less than epsilon by our setting of parameters. Okay, so if there are at most 2 bad xi, then look at the roots of those subtrees, ui. Each of those has at most 1 over epsilon bad colors. So those are colors that violate sort of this property, right? And why is that? Well, it's because the marginal probabilities of all the colors have to sum to 1. Yeah? So in total, there are at most 2 over epsilon bad colors. Yeah? Okay. So what we can do is just throw away these bad colors, and we're left with a set S of colors such that for every child I of the root and colors in that set, the marginal probability will be bounded by epsilon. And the point is that we've thrown away some 2 over epsilon colors, but assuming that delta is a large enough function of epsilon, this is still close to k. Okay? So, yeah, okay. So how do we use that? Well, we just plug it into the recurrence. So here's the recurrence that we had, and yeah. So intuitively, like where this recurrence comes from is you're asking for the fraction of colorings where the root is colored C given some boundary. But once you fix the root to be C, the number of colorings is just the product of colorings of the subtrees whose roots are not colored C. And that's where this numerator comes from. So it's just proportional to this. Okay? Okay, so how do we bound this? Well, we throw away the numerator and replace it by 1. And the denominator, we sum only over the set of good colors here. Okay? Now, what would we get out of this if the set of good colors was actually of size k instead of 1 minus epsilon over k? So we'd get a k out here. And let's assume that we actually knew a very good bound on this mu. So we knew that it was bounded by 1 over k and not just epsilon. So then we would get a term like this, 1 over k exponential of delta over k, because there's delta sort of in this product, and each of these is bounded by 1 over k. And if you plug in the bound that we're using, that k is just bigger than 2 delta over log delta, then you'll get exactly 1 over a little bit bigger than square root of delta here. Okay? So that would be sort of in the ideal case, but we're not in the ideal case. So we do a series of sort of approximations, and what we get instead is this sort of expression. So here instead of k, we have 1 minus epsilon k. Here inside, we're off by a little bit as well. Okay? But then you just take k to be large enough. So you put in 20 epsilon here instead of just epsilon, and you recover the same bound that you need. Okay? And finally, again, taking delta to be large enough as a function of epsilon, we can bound this by just epsilon. Okay, so the point of the corollary is that if at most 2 of the xi are bad, then the coloring x will be good. Okay. The second ingredient is that it turns out you can show these xi are bad independently. So the event that an xi is bad when you choose a random coloring is independent. So the way to see that is the following. So imagine the process that colored the tree on the way down. So you started with some color, you chose colors for the children, and then you propagated down, and now you're asking, what's the chance that this coloring x1 is good, given that the coloring x2 is good? You want to know whether these are independent, so you'd like to know the conditional. Okay, so the way to see it is, well, let's fix what the colors are at these ui. Okay, now once I do that, the event that x1 is good is independent of the event that x2 is good. Okay, for every good coloring x1 that I have here, I have an equal number of good or bad colorings on the other side. Okay, so these are independent once I condition on the colors here. But now the observation is that the event that xi is good is really independent of what you fix here. Because for every good coloring that you have here that started with green, there's another one where you could have started with red and it would have been good, right? So that's sort of the high-level argument, and essentially you can show that the events that these xi are good are independent. And what that lets you do is sort of write out the binomial and say, inductively, I'll assume the probability of xi being good is sufficiently large, and then you get that x is good with sufficiently high probability. So the case you're worried about is the base case. Now the base case, what happens is you have a single vertex, and you're coloring its delta children from k colors. Okay? And now what does it mean for this coloring to be good? It means that the marginal probability here for any color should be at most epsilon. Okay? Now, what is the marginal probability at this vertex? Well, I claim it's either 0 when one of the colors occurs here, or it's 1 over the number of available colors. So you just use a hefting bound and say, well, the number of available colors is not going to deviate by too much from its expectation. And that'll happen with probability exponentially. The bad event will happen with exponentially small probability so in the exponent you have something that's related to the expectation, which we know is about square root of delta. Okay, but essentially the idea is that you can certainly achieve this bound in the base case. Okay, so the conclusion of that is that colorings at the leaves are good with high probability. And yeah, okay, so we're almost there. So the last thing we want to do is show the concentration of the random variable. So here's the idea. We're going to use a martingale argument. Okay, we know that a random coloring of the leaves satisfies this good property. So we're going to say, well, what's the effect of changing one of the leaves? Okay. So suppose that X is a random coloring whose leaves are colored X1 through X delta to the L. Okay. And we're going to define sort of a partial coloring, X less than or equal to I. And the partial coloring agrees with X on the first I leaves. Okay, and the rest are just free. So the point is to move from this completely fixed boundary to the unconditional one by changing one leaf at a time. Okay. And now we write out this conditional probability. So what's the probability of the root being C conditioned on this partial boundary? And this is nothing but the expectation of the indicator. Okay, so we've got it in a form where it's just a martingale, and we can use the following martingale inequality. So suppose there's a bad event, so that the martingale differences aren't bounded. Okay, then you can just add that probability in to the usual tail probability. Okay, so what we're going to do is say that in the event that the coloring X is good, these martingale differences will actually be bounded. But we know that the probability of X not being good is exponentially small. Okay. Okay. So here's sort of the statement that we actually make. So I said that you need a slightly stronger property from X. So it's not quite sufficient that you just bound the marginal probability at the root. Instead, what you say is, if you go up epsilon L levels, then with very high probability, for any vertex V above level epsilon L, the conditional probability is bounded by 1 over square root of delta times delta of the epsilon. In that case, these differences are bounded by some constant over delta to the half plus epsilon over 4 whole to the L. Okay, so just repeating what I said before, the idea is that creating one difference at distance L away from the root causes only this much of a change in the conditional probability at the root. Okay, so now we plug this into the martingale inequality, and we get that we trade off delta to the L possible differences against the square of the difference that we're showing. Okay, so what's going to happen here is that delta to the L gets cancelled by this delta to the minus half L squared, and we're left with just a little bit more. So we're left with delta to the minus epsilon over 2 times L. Okay, which will go up to the numerator. And here's the probability that the coloring that we chose is actually not extra good. Okay, and then by choosing the parameters appropriately, we get the bound that we claimed. Okay, so maybe I won't go into how we do the bounded differences, but okay, I'll just say a few words about it. So the idea is just to use the recurrence. So, we have a recurrence for the conditional probability of a color at the root given some boundary. So we just write out these differences in terms of the recurrence and get this sort of recurrence in terms of the differences at the children. Okay. Okay, and then it's a matter of using the properties of extra good colorings. So, okay, and yeah, just finally some conclusions. So some problems that remain are closing the gap between reconstruction solvability and non-solvability. Another question is, can we show rapid mixing below the uniqueness threshold on the tree for the free boundary. So you want some number of colors that's less than delta. So say, take some constant times delta over log delta. Take a constant as large as you want. Can you show rapid mixing? And lastly, Montanari and Gershenfeld recently gave sufficient conditions for when reconstruction on random graphs is equivalent to tree reconstruction. And they showed that for the Potts model, when the temperature is larger than 0, that these two are equivalent. So can such a statement be made for the case of colorings?
Questions? What is the gap again?
Yeah.
After slides, there's after
So the gap is k times a constant. Oops. Did I? Yeah. So the gap in the degree is k times I think log 2. I guess. Yeah.
So do you see a priori that non-reconstruction and reconstruction is monotonic in K?
No, I don't think it's clear.
Because so one way of closing the gap would simply to be to prove abstractly that for each delta there's some K, and then this would give pretty good asymptotics for what the K is, and then you could say the gap is closed.
Yeah, so I don't think any monotonicity is known.
For easing, was shown that for coloring and stuff.
And for rapid mixing, I guess below uniqueness means you want to get up to delta over log delta.
Yeah, that's right. And polynomial, I guess, is known.
Right.
And yeah.
So the relationship between reconstruction and rapid mixing is conjectural.
So
Or one way, you said one way it goes.
The spectral gap of block dynamics can be bounded if you know decay of correlations, but it's in the comparison to block and Glauber dynamics that.
That is okay for monotone systems.
Sorry?
So for monotone systems, one can do the last step. Go from block.
Yeah. Also, though, because you're below uniqueness, you may not necessarily connect with Glauber for the block moves. So I don't know if.
The moment you have contraction for the blocks are bounded size.
Right, but because you're below delta colors, if you try to simulate the block moves with Glauber, you may not be connected. Yeah, right. Yeah.
So let's thank Nayantara and also the organizers, Yuval, Mark, and Elchanan, somebody who's here in spirit, and the staff. And thanks.